Okay. Okay. So I see more people now. So let me just say again that I've sent on the chat, as you can check, a link to an overleaf document, which is basically this document. Okay, so you have all the notes accessible, and so this hopefully should help you. Let me mention that they are not finished, so especially towards the end of the document is incomplete. So you can already use the document for at least the 3 first days, where the lectures are mostly complete, the document as well. But I will update this document during the week, so do not hesitate to check it again at the end of the week to get the updated document. Okay, perfect. So let's start again. So just with this new way of proceeding, in the sense that I will go through the document like this, let's just, in order for you to be able to focus of what I'm actually saying, while I'm talking about some part, I will emphasize it like this or like this. So do not try to read all the page. These are not slides. I'm really working on the document. So don't try to read everything. Just listen to what I'm saying, and just focus on the definitions that I'm emphasizing at a given moment. Okay. Perfect. So let's just recap quickly what we did this morning. We introduced Bayesian inference, okay, which is a framework to perform statistical inference, combining data, which is modeled through the likelihood distribution, together with prior information we may have about the unknown parameters to infer. And this is done through the prior. We combine the two through the post-error distribution, and then we have this probability distribution, which we need to use somehow to make inference, so to get really an estimator for the unknown parameters. This is what inference is estimation. And so what we've seen is that there is a formalization of how to make optimal decisions from the Bayesian perspective. This is called Bayesian decision theory. And what we've seen is that first we need to define a notion of loss, right? I cannot remove a notion of loss. You remember loss function, which defines our notion of distance of discrepancy between the true parameters and our estimator, our decision, delta, and the true parameters x. And unfortunately, this loss cannot be computed because it depends on the unknowns, but we can define the risk, which is the average with respect to our best guess of what the probability distribution of the unknowns are given the data, which is the post-error distribution. So from there, we defined the risk, okay, which is the average of the loss with respect to the post-error distribution, right? And once we have this risk, we were able to now give a sense of what is an optimal estimator, an optimal decision. This delta star, that depends on the data only, is the minimizer of the risk for a given loss, okay? And this is computable because it only depends on the data which we observed, which we have. It does not depend anymore on the unknowns that we're trying to infer, okay? Because we averaged over it here. Perfect. So we have this this notion of optimal estimator, which is related to the post-error distribution. The question now is to study these optimal estimators, is to try to get to quantify the performance of such an estimator. Okay, and what we are going to see in this lecture is that one way to quantify the optimal performance one can aim for is to go through a notion of that quantifies the amount of information contained in the data. It's called the mutual information, and this is deeply related to the Shannon entropy. These are basically the fundamental objects in information theory, and we're going to introduce them in this lecture. So now we introduce this notion of quantification of information content in the data about the signal, and we will see at the end of the lecture that if we can access this information content, you can compute directly the performance of Bayesian optimal estimators. Okay, so this is really the goal. We're going to connect information to performance of optimal estimation, right? So like the first lecture, if some of you are not shy and would be kind enough to show their faces, it would be really great for me. I would be very happy if you wish to be present with me in the room, so that I don't have the impression to talk to just a computer. No one is wishes to show themselves. Thanks a lot, sir. Nice to meet you. What's your name?
My name is Moti, sir.
Nice to meet you.
Thank you, sir. Nice to meet you too.
All right, thanks a lot. That's very, very nice to see real faces. All right, let's go in this new topic. So information theory. I'm going to assume essentially almost no knowledge, so bear with me. Hopefully it should be simple enough to be understandable in a self-contained manner. I'm going to not be fully formal. My focus really is for you to understand the concepts, okay, rather than all details of every equations. This is impossible for this kind of courses. Then when you want to go to the details, you have references, you have more details in the notes. But what is important to understand is what the notions I'm going to discuss mean, okay? And how do they connect to each other. All right, so information theory is really the theory of what information is, and we will first give a meaning to information, a mathematical meaning, and then we're going to connect that to statistical estimation, to statistical inference. Okay, the information theory was born in 1948 and was developed by Shannon, Claude Shannon, who was an engineer in MIT at the time. And really, this paper laid down all the foundations of modern information theory, which are at the core of signal processing, communications. All the numerical world is essentially a consequence of these notions we're going to discuss. All right, so let's be very concrete and define right away the most important quantity in information theory, the most basic one, which is the so-called Shannon entropy. Okay, so this is a quantity introduced by Shannon in this paper, but the name entropy was already there for a long time. So for those of you who know a bit about physics, and in particular statistical physics, the notion of entropy is already there for at least a century in statistical physics, okay? And the reason why Shannon called his definition of, we will see, information content entropy is not by luck. It's precisely because this quantity is fundamentally linked to the notion of entropy in statistical physics. I will not develop in this lecture this notion, but we will see in the next lectures that indeed what we call entropy, free energies, quantities like this in statistical mechanics are really linked to the same notions in information theory. These are basically two sides of the same coin, okay? All right, so let's start by just defining the entropy. So the entropy of a random variable, so I will consider at the moment only discrete valued random variables. So here is x, a discrete valued random variable with probability p. And I will call, so I will be slightly loose in the notations. I will both call the random variable itself capital X, and I will also call its possible outcomes with the same notation. But given the context, it should be clear whether I'm talking about the actual random variable or one of its outcome, okay? For example, it's inside a sum or an average. I'm talking, so for example, here, if I'm summing here, of course, these are the possible outcomes, the possible values that this random variable may take. If you see a quantity like this, expectation with respect to x of some function of x, here the x in the argument should be thought as the random variable because I'm averaging over it here, okay? Perfect. So the Shannon entropy associated with a random variable or equivalently associated with its law, because this is only a function of the law of the random variable, is the following. It's a sum over all possible outcomes of the variable of their probability times log of 1 over the probability, okay? So this can be interpreted as an average. You see that this operation there is an expectation. It's the expectation with respect to x. It's the expectation with respect to x of, not, sorry, without the log here. This is the expectation with respect to x. And it's the expectation of what we call the information content or surprise. So let me define this little h of x as the log of 1 over p of x. So here, in this case, the x should be thought as a possible outcome, okay? So, for example, if you have a coin, the outcome could be a head, okay? While the random variable is the coin that can have head or tail as outcomes, okay? So the surprise associated with an outcome is the log of 1 over its probability. So why is that somehow natural as a notion of surprise? Because you see that if an event, an outcome, has a low probability, so p of x is close to 0, then log of 1 over something that is close to 0 is large. So if an event has a low probability to occur, then its associated surprise is high, in the sense that if you would observe this event, this outcome, you would be highly surprised because it's simply an unlikely event, okay? On the contrary, if p of x is close to 1, so if an event is highly likely, then its surprise is low because you get log of 1, something, you get something close to log of 1, which is essentially 0, okay? So highly likely event have a low surprise. Of course, you could define many functions with this property in the sense that it would be high when p of x is close to 0 and 0 when it's close to 1. There are infinitely many choices of functions that would verify this property, so this is not enough, of course. But this is already an indicator that this is a valid candidate of what we could call the surprise, okay? And you see the entropy is therefore the average surprise, right? I can rewrite this as the expectation with respect to x of little h of x. The entropy is the average surprise, okay? So you can define, by the way, the entropy with different normalizations for the log. So this is the log in natural units. In this case, the entropy is defined in terms of what we call nats, which stands for natural units. If you take a log 2, the entropy would be written in bits, okay? Perfect. So let's now give some more meaning to the entropy. So I would like to essentially convince you of the following facts. Okay. The first fact I want to convince you is that the Shannon entropy defined before can be thought as its average information content, namely the expected information gain when observing the outcome of a random variable. So conceptually, you can think of a random variable, as long as it's random, it hasn't taken any value, so you haven't observed the outcome of this random variable, so it is an uncertain object. Okay. Basically, the entropy can be thought as how much information would you gain if you observe the outcome of this random variable, and this in average over all possible outcomes. Okay. So imagine the following experiment. You are in the desert. You're walking. Okay. And you observe that it's raining frogs. Okay, suddenly it rains frogs. This is slightly weird, right? So it is a highly unlikely event. The fact that it rains is already unlikely in a desert, but the fact that it rains frogs is even more unlikely. And this is so unlikely that actually it should make you realize that you're probably dreaming. Okay, so you see this event is very unlikely, and therefore it has a high informational value. The fact of observing such an unlikely event brings you a lot of information. Okay. Now suppose the opposite. You are in the desert and it's very sunny and hot. This is a very likely event, given that you are in the desert. So even if you were dreaming, you would not realize it, right? Because the fact of observing hot weather in the desert is extremely likely, and therefore has a low informational value. The fact of observing this outcome of the random variable weather, the weather in the desert, would not bring you any information, and yet additional information that you already have, the fact that you are a desert. Okay, so if you are averaging all these information gains associated with all the different outcomes, you get the average information gain, and this is the entropy. Okay, but you can also think the entropy the other way around. You can think of the entropy as the average uninformation or lack of knowledge about some random variable. So it sounds weird because it seems that I'm telling you right now the opposite. I just said that the entropy can be thought as potential information gain. How much information do you gain in average when you observe the realization, the outcome of a random variable? Now I'm telling you that you can also think of this as the average lack of information, the amount of how much do you not know about a random variable. But this is exactly the same. It's just a conceptual shift, because the information that you gain is what you gain when you do observe the random variable outcome, right? But prior to observing the random variable, you actually do not know a lot about this random variable. And the more this random variable is unpredictable, in the sense that the more some events are unlikely to happen compared to others, the more you know, the more you would gain when observing it in average, because potentially you will observe unlikely events with a high informational value. But at the same time, it means that before observing the realization of the random variable, you know less, right? So essentially, the fact of observing the outcome of a random variable converts a certain amount of uninformation, of lack of information, into information, okay? So it's just conceptually placing yourself before or after having observed the outcome of the random variable. Okay, so you can equivalently think about the Shannon entropy as the potential, the average information gain that you would get when observing the outcome, or equivalently as the average uncertainty, the average lack of information about the random variable. Okay, these are just the same thing, right? The entropy is quantifying, so from what I just said, the amount of unpredictability of a random variable. So essentially, the higher the entropy, the less you know about this random variable, about its outcomes before observing it, and therefore the more unpredictable it is. Okay? So what is a variable with the smallest entropy? So which is the less unpredictable, or the more predictable, if you wish. It's simply a deterministic variable. It's a variable that always takes the same value. It's not random. In this case, the entropy would be 0, because without having to observe it, you know in advance what value it takes, because it does not fluctuate. Okay, it cannot take any other value. The extreme opposite is the uniform distribution. If all outcomes of a certain random variable have the same probability, in average, it is the most the one that brings the highest surprise in average. Okay, so it is the most unpredictable, essentially, because any outcome can happen with the same weight, so you cannot say much about it before observing it, right? Okay, so this was for interpretations of the entropy. Let's now see formal properties, mathematical properties of it that suggest that what I'm saying makes sense. Okay, that this is the right notion of information content carried by a random variable. Okay, yes, here I want to mention one thing. The entropy h of x is the expected number of yes-no questions that you would answer when observing the outcome of a random variable. Basically, or the other way around, if you do not know the outcome and you want to know, let's say someone observed the outcome of a certain random variable, the weather in some place in India at a given day in some region. So this was observed by someone that therefore know the outcome of this random variable. From your perspective, this is still a random variable. You don't know this weather yet, and you're trying to guess what was the weather on that day. So you start asking to that person questions of the yes/no form. So was it raining? No. Was it hot? No. And you can ask a number of questions until you get to the answer. Okay. And basically, the entropy of a random variable quantifies how many such binary questions you would need to ask to identify with certainty the outcome of this random variable. Okay? Okay. Perfect. So this I already said. The entropy is never negative, by the way, from the definition, you can check. And it is equal to 0 only if the random variable is not random. It is a deterministic variable, meaning that there is a single outcome indexed by I here that would take all the probability mass. So Pi would be equal 1 for a certain I. Okay. In this case, the entropy is 0. There is no uncertainty about it, or equivalently, observing it would lead no information, that additional information that you don't already have. Okay. And like I said, the entropy is maximized for the uniform distribution. Okay. Only when all outcomes have the same probability, which is 1 divided by the number of outcomes, which which is this symbol here, then the entropy is maximized. Okay, so there are some nice properties that we can show for the entropy. In particular, the fact that it is the average of the surprise here, minus log x, implies something nice. If you take two random variables which are statistically independent, so this notation means that the joint law of x and y is just the product of their laws, then the surprise is additive. Of course, you have minus log of p of xy equal minus log of p of x times p of y for independent variables, which is minus log of p of x minus log of p of y. So the surprise is additive for independent random variables, and therefore the entropy as well, because it's just the average. The average is a linear operator, so the average surprise is as well additive if the surprise itself is additive. Okay? So what does it mean? It means that if x and y are independent, the total information carried by observing both is the sum of the information carried by x only plus the one carried by y. Of course, they are independent. Okay? This entropy there is defined as before. So this is called the joint entropy. So it is the very same definition, except that now we're talking about more than one random variable, in this case a pair, but actually the definition has to be the same because you can always think of a pair or any vector of random variables as just a single one random variable, but it's just a vector. So the definition is the same. I'm summing over all possible outcomes of this pair of random variables of the probability log of 1 over the probability. Okay, so this is the average surprise carried by the couple of random variables. So it's called this is also called the Shannon entropy, but for the pair. Okay, let me define another notion of entropy, which is important, which is called the conditional entropy of x given y. So the conditional entropy is defined similarly, except that now, you see, I'm averaging with respect to the conditional law of x given y log of 1 over p x given y, and I'm averaging over y as well. I can also write this as the joint law. Okay? So the meaning of the conditional entropy is the information like the expected information gain when observing the outcome of random variable x, given that you already know the outcome of y. So how much information can you still gain when observing x if you already know y? Or the other way around, again, there is the unpredictability interpretation. This is the remaining uncertainty about x, given that you already know about y. Okay? Very simple. Okay, so a very nice property of the entropy is the chain rule. So the chain rule is telling us that the total information carried by the pair of random variables xy can be decomposed as the information carried by y alone plus the remaining information carried by x when you already know y. So you see, this tells you what y brings, and this tells you what x brings that remains, right? So this equality is very natural. But of course, I recommend you to try to prove it. It's very simple, and it just follows from the definition that I gave before. It's a one-line proof. But you can also write it the other way around. So the total information is the one carried by x plus the remaining one carried by y, given that you already know x. Okay. Another important property is that this is a form of what we call a data processing inequality. So if you apply a certain function to a random variable, any function, okay, you can only decrease the entropy, or at best do not decrease it. It can remain equal, but you cannot increase the entropy by applying a function to a random variable. So basically it means that whatever random variable, you can process it in any way, you can apply any function you want. The total amount of information carried cannot be changed. It's a kind of conservation of information. Okay, you can only lose information. You cannot create information out of nothing. Okay, it's a bit like energy in physics, if you think about it. And actually, there are many parallels between energy and entropy. Okay. Okay. And the equality here stands. So this is an equality if and only if f is invertible. Okay, if you can uniquely invert this function, then considering the original variable or the processed one, it gives the same amount of information when observing its outcome, because you can go from one to the other in a one-to-one way. Okay, another property, if two random variables are independent, again, then the conditional entropy is just the entropy. Again, once you have absorbed these notions, what entropy means, you don't even need to prove this. It's kind of direct, right? The total unpredictability about x given y is just the one of x if x and y are independent. It has to be the case, and indeed it is. You can prove it. Okay. Finally, let me emphasize this last property. The total information carried by a pair of random variables is less or equal than the sum of the information carried by both. Okay? So again, this is an equality if and only if x and y are independent. And the fact that we have an inequality in this direction is natural, right? Because again, if x and y depend on each other's, okay, if you observe one of them, it already tells you something about the other. So it reduces the potential information gain carried by the other. So the inequality has to go in that direction, okay? Okay, so before moving to the next definition, is there questions on the entropy? Okay, so I guess these are notions that you're familiar with. Perfect. So let me now move to slightly different thing. Let me just mention quickly here, even if this is not so important for the rest of the discussion, but
excuse me, sir.
Yes.
Can you please explain the last statement? What you explained?
Here?
Yeah, this one.
Yes. So I'm saying that you see, you have an inequality that tells you. Let's think in terms of uncertainty. Maybe this is conceptually simpler. What is the total uncertainty about a pair of random variables? It has to be less than the uncertainty of one plus the one of the other. Because you see, if the variables depend on each other's, when you measure one, when you observe one, it tells you something about the other. So it reduces the uncertainty about the second one. So that's why the inequality goes in that direction. Instead, if the two random variables are independent, this is an equality, okay? So I don't know if this is clear, but when random variables are dependent on each other, observing one tells you about the other, and therefore you you can only get a reduced uncertainty. So maybe I can prove it. This, you can see it like this. Let me prove it. So take the chain rule. Okay, we have the chain rule there. And what I'm saying is that, so I write the chain rule, which is h of x, y equal h of x given y plus h of y. And what I'm saying is that this is necessarily less or equal than h of x. The uncertainty about x given y is always lower than the uncertainty about x. Basically, observing something cannot reduce the amount of information. So you see, the fact of observing something has to reduce the uncertainty. This is information. An observation is information. So you have to reduce the uncertainty. Is this inequality clear?
Yes, sir.
Okay, so I'm using this inequality from the chain rule to show this one. Okay? Perfect.
Okay, sir. Got it. Thank you.
Perfect. Thank you for the question. Let me just mention that everything I said is kind of, let's say, exploiting the fact that we're working with discrete random variables, but you can generalize the notion of entropy, of Shannon entropy, to real valued random variable. And this notion is called the differential entropy. Okay, so the differential entropy is defined similarly. You see that we have a kind of surprise here. This is the log, this is minus log of the density of the random variable. And I'm averaging over it with this integral against fx. Okay, so so this is the natural generalization, but one has to be a bit careful, because with continuous variable, for example, this differential entropy is not necessarily non-negative. So the Shannon entropy of a discrete random variable cannot be negative, and so this is a natural property one wish for a notion of information. There is no such thing as negative information. You cannot lose information by observing something. However, the differential entropy can be less or equal than 0. Okay, so it's a bit less natural to think of it as an information content. However, for continuous variables, there is a slightly different object which will recover the correct, let's say, properties that make it a good candidate of information content. Instead of working with entropies, with continuous variables, we will work with differences of entropies. Okay, and this will be the mutual information, and this is the correct notion to work with when you have continuous variables. We'll do that now. Okay, so in order to define the mutual information, I first need to define another thing, which is the Kullback-Leibler divergence. Okay, the Kullback-Leibler divergence is defined like this for discrete or continuous variables. So this is again an average over some probability distribution P of x of the log of the ratio between two probability distributions. Okay, so this is for the discrete case, and you have the continuous case below. So notice that this this definition is non-symmetric, which is emphasized by this symbol here, this double bar. The fact that P is on the left and Q is on the right here means something. Okay, if you were putting a Q there and a P there, you would have a Q there and a Q there and a P there. So this is a non-symmetric definition. Okay, so the meaning of this object is a kind of measure of inefficiency of assuming a certain distribution when the true distribution is P. So what does it mean, this concretely? It means that if you are trying, so let's say you are sampling the distribution P. You obtain outcomes from the random variable whose distribution is P. So let's say there are sequences of numbers or of words, okay? And you're trying to compress, using some compression algorithm, these sequences, but as using a compression code. So it's an algorithm that tries to find a more compressed representation of these sequences without losing information. So you're just trying to find the proper representation such that with less symbols, you can kind of keep the same amount of information carried by these sequences. But you're using a compression code that was not optimized for samples from the distribution P, but instead for samples drawn from the distribution Q, which is different. So your code is not optimal for P, it is optimal for Q. So you are not using the right compression code, if you wish. And this DKL is kind of telling you how many bits you are going to use by using this compression scheme that you could have kind of not use if using the proper compression optimized for P instead. Okay? Okay. So it's a measure of essentially how distances, like how probability distributions are far from each other, that you can think in terms of compression. Okay. By the way, as I mentioned in the lecture notes at the beginning, if the kind of things I'm saying here are really new to you, I'm sure that everything I'm saying is therefore not so trivial. And there is an amazing book that I recommend, which is by David McKay, that you can find on internet, which is free on his website. There is a link on the notes I give. And you have tons of examples, very detailed. It's extremely clear. This is really one of my favorite science book for information theory, inference, machine learning, for tons of things. So I highly recommend it. Okay. So for example, if you compute the KL divergence between two Gaussians, let's say they have the same variance, but they have a different mean, mu1 and mu2, what you obtain is the following formula. So you see that it diverges as a square of the difference between the means, okay? Okay, so this KL divergence has a number of properties. So in particular, this is not a true distance because the distance is always symmetric. The distance between point A and B, so here the points we're talking about are probability distributions that live in the space of probability distributions. If you take probability distribution 1 and 2, 2 points, a correct notion of distance between the two is that the distance between the first and the second is the same as between the second and the first. This is not a symmetric object, so this is not a distance in the geometrical sense. This is something else, but this is a notion very useful. It has a number of properties that I won't discuss, you can take a look, but in particular, it's never negative, okay? It's only 0 if P equal Q. So it's not a distance, yet it is 0 only when these distributions match. So it shares features with distances, okay? Okay, now, let's move towards notion which will be really central to this course, which is that of mutual information, which is the following. So we will see that through this notion, why is it central? We will see that if we are able to compute this mutual information that I'm going to define now, we will have directly access to the performance that one can aim for in the best possible case, the performance of Bayes optimal estimators that we define through Bayesian decision theory. And this is really the ultimate goal of this course in the context of high dimensional inference. Okay? So this is really a key object. So let me define it. Take a pair of random variable xy, okay? The mutual information, which is a symmetric notion now, okay? Contrary to the Kullback-Leibler divergence, the mutual information between x and y is the same as between y and x. And this is the reason why people use a dot comma here. It's to emphasize the symmetric nature of this object with respect to its arguments. Is by definition the Kullback-Leibler divergence between the joint law of the two random variables and the product of their individual marginals. So just that we're on the same page to make sure that some notion is not missing to you. What is the marginal of a probability distribution? So if you have a pair of random variable, you can obtain the marginal of x, let's say, by integrating with respect to y their joint law. Okay, so this is the marginal. And of course, you can obtain the one for y by integrating with respect to x. And this operation is called marginalization. Okay? So you are looking at how different, in the Kullback-Leibler sense, is the joint law of the pair, when you really consider them together, how different is this distribution from the product of their individual distributions, as if you were considering them independent. Okay? So it is from the earlier definition, we get this definition here. So this is the average with respect to the joint law of the pair of the log of the ratio between the probability of the pair divided by the product of the probabilities of the individual events. Okay? You can also define the same thing for continuous variables by replacing this sum by integration, and these probabilities become densities. Okay? But the definition is the same. So, okay, this is a bit an abstract definition. Let me try to convince you now again with words. Why is this a correct? Why is this a nice object to look at? Why is it so important? So again, you can really think of it as a kind of distance between 2 points, where these 2 points represent the joint law of the pair and the product measure. This is the product of the marginals. And the more these 2 points are distant from each other somehow, the more these two random variables should depend on each other's, right? Because here it means you are forgetting the dependence between the two. Here you are considering it. And if this distance is big, it means that they are strongly dependent on each other's, because it means you cannot approximate the joint law well using the product of the marginals. Okay? If two random variables are weakly dependent on each other's, it should be a good approximation to consider their joint law as just the product of their individual laws. In this case, this Kullback-Leibler divergence would be small. But if they are strongly dependent on each other's, it should be high. So it measures this, the amount of dependence between random variables. Let's now use our understanding of what Shannon entropy is and place ourselves in the context of signal processing, signal extraction, of inference, in order to make more sense about this quantity. Okay?
So I want to ask a question. So
Yes.
Earlier, when we were doing KL divergence between P and Q, we were talking about like how much more bits we needed to encode samples from P using the encoding scheme optimized for Q. So
Yes.
in this case, in the information sense, what does it mean that we are like in the information definition where we are doing care divergence between the joint and the marginals.
Yes.
How to think of it in terms of codes?
Yes.
Is there a way? Yes,
Yes.
I just wanted to ask.
Thank you for the question. So let me try to. All of you, please stop me when you have questions. I mean, that's really the point of these lectures. So thank you for the question. So if you want to think in terms of codes, you see, this kind of quantifies the additional number of bits you will need to code if you were. So imagine the following experiment. You are generating sequences of pairs of random variables like this. So you have realizations of xy. So you have the first realization, you have xy11, x2, y2, okay, xn, yn. These are realizations of the pair of random variables, okay? And you are trying to compress these sequences. Think of this as the first word, okay? This is the first word in a two-word sentence. This is the second word, the first word, second word. And you are trying to to code these sequences efficiently. So to find a compressed representation that allows to keep the information carried by these sentences, but with the smaller number of bits, okay? If you are assuming that the word 1 and 2 are completely independent, have been picked randomly in the dictionary, one after the other independently, then you have a certain compression code associated with this assumption. And if you try to compress these sequences with this code, it would give sequences of a certain length in bits. But if you do so, it means you are using a code optimized for this distribution. This is not a very smart choice because, of course, there is a structure in a sentence. The second word is not picked randomly after the first. For example, if I tell you I, there is a higher probability to pick the word am or I do rather than car or dog, right? So if you're kind of forgetting these dependencies between words and use a code optimized for the cases where the words are picked independently of each other, this would be a bad code. The compression would be not good. And the information, the number of bits you would require in addition that you should not need if you were exploiting the correct dependencies between words is quantified by this. Does it answer your question?
Understood, sir. Yes, sir. And the reason, like, we could have the P and Q places swap in the mutual information. It's just specific reason why the joint is on the P side and the marginal products are on this Q side of the K and divergence.
Exactly.
Is there a specific reason?
You mean why we don't put it the other way around?
Yes, sir.
Because if you do so, you will lose the identities that I'm going to write next. This is not the correct definition. There is no short answer. It's just that what I'm going to say next does not apply, and therefore this is not the correct one. Okay?
Thank you, sir.
Okay, thank you for the question. So let me continue. So if now we have two main definitions. We have the Shannon entropy at the beginning. We have the Kullback-Leibler divergence. You take these two definitions together and the mutual information, three definitions. What you realize directly is that the mutual information can be written in terms of Shannon entropies. In particular, the mutual information between x and y is the entropy of x minus the conditional entropy of x given y. So let's think again as x as the unknowns, or what you call in signal processing the signal, and y is the data, and it's a function of x, is the observed data. Okay. This interpretation, this identity is then very natural. Okay, what does it tell you? It tells you that the mutual dependence between X and Y, so essentially the amount of information carried by the data about the signal, or vice versa, because this is a symmetric notion, but I think it's more natural to think as the data carrying information about the signal, is what? It is the uncertainty about X, okay, so how much you would potentially gain if observing X, which is equivalently the amount of an unpredictability about X. So this is the uncertainty about X minus the uncertainty about X that remains when you observe the data. So it's essentially a reduction in uncertainty, okay? So if Y, the data, is independent of X, this is simply equal to that. So observing the data would not reduce the uncertainty about X, and therefore the mutual information would be 0. Okay? So the reduction in uncertainty about the signal when observing the data would be 0 because they would be independent. Okay? So this is the first notion, the first interpretation. It's uncertainty reduction due to data observation. But you can write it the other way around. You have also this equality, you can do it. What does this say? It tells us, now instead of thinking of uncertainty, I want to use the dual meaning of entropy, which is information gain, okay, the information content. The mutual information between my signal and data is the total information carried by the data, okay, minus the remaining information carried by it when I already know the signal, okay? But what does it mean, this object? If I already know the signal, what is the information carried by the data? What does it even mean? It's simply the contribution due to noise. We're always thinking of a noisy process. You have a signal which is corrupted by noise, and then the data is this noisy version of the signal. And so there is part of what Shannon calls the information, which is also related to the noise. You cannot forget it. We call it as noise in a given specific problem because this is the component that we do not care about. But information theory is agnostic about what you, for a given problem, care about or not. It's still something which is in the data. Okay, so the notion of noise is a subjective notion. What is signal, what is noise depends very much on what the task that you're studying, okay? Maybe for someone else, given the same data, they want to reconstruct what you call the noise, and the signal for you is what they do not care about. So it's subjective, okay? So thinking about X as the signal and the remaining in the data as the noise component, this term is precisely quantifying the information carried by the noise component. That is what remains when you already observed what you call the signal X. Okay? So this is the total information carried by the data minus the information about the noise. And so if you remove the information carried by the noise, it means that this is indeed the information carried by the data about the signal only, because you remove the noise component. Does it make sense? So this is the noise component or contribution to total information in Y. And so if you, this is the total information. So if you remove the noise component from the total information, what remains is what the data tells you about the signal only. Okay? So it's a very natural object to look at. Okay, perfect. So Jaspal, can I do 10 minutes more, or is it too late? Okay, we'll assume the answer is yes. So let me continue. Because I think that the lectures are basically between 1 and 1 hour 30. So let me take a tiny bit more of your time. So let's define. Let's see additional properties of the mutual information. First, let me just define the conditional mutual information. That is, what is the mutual information between X and Y conditional on a third random variable? And this is just the same as before. It's the KL divergence between the joint law of X and Y given Z and the product of their marginals given Z. Okay? So this is the very same definition as before. It's very natural. And again, you can write down this as difference of entropies, or differential entropies if you're working with continuous variables. But the interpretation is the same. It's just that now everything I just said applies, but given the observation of another third random variable that was already observed. Okay? But it's the same. So some important properties: the mutual information is symmetric by definition. It is non-negative, and now this is always non-negative, including for continuous random variables. So this is what I meant by this is the correct notion to keep in mind for information content, including for continuous variables, because this is always non-negative. So now you are kind of looking at Shannon differences, and the fact of working with differences makes the entropy the correct notion of information carried by one variable about another one. Okay, you are comparing. An important property is the data processing inequality. So it tells you that if you have a Markov chain, so Markov chain means that so this symbol means that the probability distribution of X, Y, and Z can be written as the probability of X times the probability of Y given X times the probability of Z given Y. In general, here I could put an X as well, but if you already know Y for Z, you don't need to know X anymore. It becomes independent of X. So this is what a Markov chain is. And the data processing inequality tells you that the mutual information between X and Y has to be at least the one between X and Z, which is very natural, because in the middle there is an operation that happens there. And you cannot increase the information. Okay, this is what we mean by data processing inequality. You can only decrease information. Okay, so in the best case, this Y is a invertible function of X. It's a one-to-one function of X. In this case, the mutual information between X and Y and X and Z would be the same. But if it's not invertible, you would lose something. Okay, if this step has some noise, if you want, you would lose some information. Like for Shannon entropy, we have the chain rule. Again, by definitions, you can try to prove these properties. It's very simple. So the total information carried by the pair YZ about X, or vice versa. Notice that here there is a dot comma here, while here it's a normal comma. So it means that we're computing the mutual information between X and the couple XY, which is like one random variable. This is the total information, this is the mutual information between X and Y, plus the remaining information carried by X about Z, when you already know Y. Again, it's the same type of decompositions like for the entropy. It's very natural. Okay. Okay. maybe we should stop there, and at the beginning of the next lecture, I will show you this very important result, which is really what motivates this lecture of introducing mutual information and all that. The reason we will see is that if one knows the mutual information, you can take a certain derivative of it with respect to the so-called signal-to-noise ratio. I will introduce that better at the next lecture. You directly access the minimum mean square error. Okay, this is the error between the signal and the base optimal estimator, which is the posterior mean. You remember first lecture, Bayesian decision theory. The posterior expectation is the best estimator in the universe if you are considering the Euclidean distance as a loss, which is what I'm considering here. So this is really the goal. We want to compute this quantity, which will lay down fundamental bounds to the performance of any inference procedure. But to compute it, we will first need to access the mutual information. And then by derivation, we will get it. Okay? Perfect. So we'll repeat that next lecture. And so we see each other's in, I guess, in 45 minutes. Or Jaspal, are you here? Okay, so let's disconnect and let's reconvene at the normal time, which is which for you is 4:30. Okay, which is in, what time is it for you? Which is in 50 minutes. Okay. Is there any question or? Okay, no question. So I assume that it was clear. So see you in less than an hour.